Hello and welcome everybody to this lecture on inverse problems in medical imaging. So topics for today. First of all, we discuss numerical derivatives because Kerstin started with you solving nonlinear inverse problems where she used derivatives implicitly, and now we're going to use numerical derivatives. And number two for today will be an introduction to regularization. Let's start. So let's recap shortly what Kerstin did with you at the end of the last lecture. I'm pretty sure she talked about nonlinear forward problems written down in the style or whatever. And the aim was to linearize the problem and then solve the linearized problem with the algorithms and the ways we do know already. So there came up this algorithm. It said, first you should pick a starting model vector. And this model vector is not, or starting model vector is not trivial. Saying if we choose like a wrong starting vector that we just diverge from step one away. Yes, this is true. This is not trivial. You can think a little bit like gradient descent or whatever, where the starting point is crucial. Number two was you should calculate the predicted data vector with the current model vector, so to say. And out of that, you should calculate a misfit vector. And number three, and this is really the important point, you should form the derivative. And in the last lecture and the example Kerstin did with you, you just know what the derivative of the function was because it was a very easy function and you could calculate it. But of course, this is not trivial. And this is actually the reason why we're going to do the lecture today the way we're going to do it. Number four is then easy again. You should solve this very easy linear inverse problem, and you know how to solve linear inverse problems already using an appropriate inverse operator. Saying an appropriate inverse operator, here you should apply all your knowledge you have already and decide on which operator fits best. Number five, now you should form the new model parameter vector M1. And then you continue with step two, and so on and so on. So this is a recap, but as I pointed out already, step three is the step we're going to focus on today. This leaves us the following aim or the following chapter heading for today, numerical derivatives. So in practice, what we really want to do is we would like to have our computers or whatever stuff we use to solve the nonlinear inverse problem automatically. But therefore, we really need numerical derivatives for solving or for building the derivative. So we introduced the concept of the finite differences today. So we're gonna do this using pen and paper once again. I'm pretty sure that you all have heard about the Taylor series expansion before. We're gonna recap it here shortly. And we use here for modeling a very simple function f at point x. So it's just a 1D function. And if we truncate Taylor after the first term, we get the following. So we end up in f of x plus h equals f of x plus first derivative of x times h. We can rewrite this. And so f of x is f of x plus h minus f of x divided by h. So I'm pretty sure all of you know how a derivative of a function is defined. Just to remember it shortly. So like the true derivative is given as the limit of h to 0, f of x plus h minus f of x divided by h. So what you see here is h will be very small, then the Taylor expansion can model your first derivative or just approximates your first derivative as good as possible. We can truncate the Taylor series after the second term as well, which would be the quadratic term. So let's have a look at that. And here we actually need two versions. First of all, we add a positive h. So we get f of x plus first derivative plus second derivative of h squared. But on the other hand, we will look at f of x minus h as well. So f of x, then we have a negative sign here, and we have a positive sign here again. Now we do some fancy reformulation. And we end up in the following, that we can approximate the second derivative as f of x plus h minus 2 times f of x plus f of x minus h. Divided by h squared. So this was for a function in one variable. Of course, the question is, what about multiple variables? So like 2 or 3 or whatever. And therefore, we look at the multivariable Taylor series. So we look again at the function f. But now we assume a 2D data set. And we would like to look at the expansion at point IB. So f of xy is then f of IB plus, and here starts the fun. We have the partial derivative of f with respect to x at point IB. So what this thing here means, we first build the derivative of the function with respect to x, so with respect to the first variable, and then once we have done it, we plug in IB. So this is multiplied by x minus I. Then we do the same thing for the derivative with respect to y. So this was the first part. Now about the second derivatives. So we have second partial derivative of f with respect to x at IB. And here we have x minus a squared. Then we have 2 times second derivative with respect to x and y. And last, of course, with respect to y squared. So here we have the constant term. Then we have the linear terms. We have 2 of them, followed by the quadratic terms. And of course, we could build further terms, but we do not do that. However, those things therein, they start to look already a bit annoying. So therefore, we introduce a compact form of representation. So we assume that the vector x contains x and y, and the vector a contains a and b. Then we can write down f of x as f of a. So this was the constant part. Then we have the vector x minus vector a transposed. Times the gradient. And then we have x minus a transposed. And then the Hessian, I will discuss in a second what this is. X minus a. And so on. So this was the quadratic terms, and then the terms of order 3 and so on can follow. So this h of x and y, or h of the vector x, or whatever notation we use, is in the case here a 2 by 2 matrix containing the second derivatives. So on the diagonal, we have the second derivative with respect to x and y. And here we have the mixed derivatives. So this is the Hessian matrix. And there's one thing I'd like you to note. We know that the second derivative of f with respect to x followed by y is the same as y followed by x. So what this means is it's completely our choice which derivative we will first. If we first derive with respect to x or y. And the reason behind that is a theorem called Schwarz theorem. And it says that you can change the order of differentiation. So what this means for you in practice, if you look at a function, you have the feeling that the derivative of with respect to one of the variables will make life so much easier, because things are constant terms, linear terms that will be constant the next time and so on. Do that first. Don't start with the hard ones, start with the trivial ones. So when we do a linear approximation, of a function in multiple variables, then we can define f of x, or we can write it approximately as f of a plus x minus a transposed times the gradient. And you see here why it is linear, because the only variable left here is x, and it is included in a linear fashion. So once you have reached this stage, there's nothing to worry anymore, because you know already all the solution keys of solving the inverse problem here. If we use a quadratic approximation, then f of x can be written as f of a plus x minus a times the gradient. So nothing has changed here compared to the linear approximation. And then we add x minus a transposed times the Hessian times x minus a. And here it's clearly visible why we called it a quadratic approximation. We have the linear term here like before, but here we add one quadratic term. Last thing that is important to note here, the formulas, those two I just presented, they do not only hold for two variables or a vector of dimension 2, but for an arbitrary number. Let's do an example. So we would like to compute a second order Taylor expansion of a function I will design in a second around the specific point 0. And we define the function as e to the x times the logarithm of 1 plus y. So the function here is highly nonlinear. Obviously, the exponential function is nonlinear, but also the logarithm is nonlinear. And we use first order Taylor to approximate or to show a linear approximation of the function, and second order Taylor to introduce a quadratic approximation of the function. Before we start, we need to discuss which partial derivatives we actually need for that task. So we have them of first order. There's two variables therein, so obviously there's two first order partial derivatives. They're df derived by dx and df by dy. And then we have the partial derivatives of second order. And from them we have three in total. So we have first the ones with respect to x, then with respect to y, and then the mixed, and we said the mixed are somehow the sign, so it doesn't really matter if we start with x or y. Okay, let's start. Derivative with respect to x, nothing changes. With respect to y, we have e to the x divided by 1 plus y. Then for the second derivative, we have e to the x divided by 1 plus y squared. And now for the last, remember we said the series doesn't matter. So therefore it's very convenient using something where we do not have to do anything anymore. And if we look at df derived by dy, and we think about deriving it with respect to x, we see that nothing changes. So we have 5 derivatives. Next, let's do that here so that you can see it. We need to do the evaluation at the points 0 and 0. So f of 0 and 0, put it up here. We have the logarithm of 1. We all know that the logarithm of 1 is 0, so therefore this is 0. Number 2, df derived by x at 0 and 0 is 0 again. So for the last one, if we're gonna plug in 0 and 0, then we end up being 1, right? Yeah. And therefore the last and the second are the same, so we have 1 here. So missing is the second derivative with respect to y. Which is then minus 1. So let's put everything together. We have the constant term. Then we add twice the linear terms. First with respect to x, and then with respect to y. And then we have 3 quadratic terms. We have the derivative with respect to x. Then we have the mixed one. And last, we have the one with respect to y. Okay, now let's plug everything in. So we have 0 for the constant part, 0 for the part with respect to x. Then we have y. And for the quadratic parts, we have 0 since the second derivative with respect to x is 0. Then we have this mixed term, and finally we have minus y squared. So we end up in being y plus x times y minus y squared half. So we started with a very complex looking function. We built a second order Taylor derivative, and we ended up in something that's not so complex anymore. It actually looks quite nice. So these partial derivatives and the numerical derivatives I introduced a second ago, you can implement very easily in whatever programming language you use. So if you need to solve nonlinear inverse problems and they do not look too bad, this is the way to do it. Okay, then let's continue with the next very big topic, regularization. I'm actually pretty sure that all of you have heard of it before, but probably we can give you a bit of a deeper insight here today and in the next lecture. As always, we try to present things to you in a way that you can understand it using examples and so on. But if anything is unclear, just interrupt us. Before we start with it, we should discuss, as always, why are we doing these things? Let's think about once again at the least squares fitting we did. We introduced it here in the lecture for a straight line. We discussed it very shortly for polynomials. And in the end, we figured out that as soon as we know the order of the polynomial, we're fine. there's two problems. First of all, how do we determine the order of the polynomial? And second, and like a bigger problem of those two, what is if we have no idea about the behavior of the data? So assume that you get completely arbitrary data. You do not have any clue on what the data looks like, and therefore you cannot really decide on the polynomial to use. And the answer to this problem, simply put, is regularization. So assume here for a second a polynomial of order m. So you have coefficient theta in there, and you have a one-dimensional input variable x, and you use it up to the power of m. And if we assume least squares fitting, like we did least squares fitting of a straight line, you can fit the data to the polynomial using the minimization problem I've just written down here. So you minimize this thing here via theta. You have just one scale factor here in front is 1 divided by the 2n. It doesn't really matter if it's here or not. It's just because it's nice. And then you sum up the areas squared of the polynomial with your input data and your actually measured data. So nothing really changed compared to before. The aim is obviously to fit the parameters theta. Now, when we say we have like an arbitrary dimension of the polynomial, we actually have three scenarios that come into our mind here. The first is the following. So assume you have those data points here, they are red dotted, and they seem to be on a quadratic curve, so on a polynomial of order 2. If you fit a straight line through it, so a polynomial of order 1, which is written or printed down here in green, you have underfitting. So you can't really fit data properly. There's just one dimension missing in your polynomial. So this would be the case with the thing we discussed a couple of weeks ago. Number 2, assume we have polynomial order 2. Then the thing here looks just right. The data seems to be on a polynomial of order 2, and we can fit the polynomial now of order 2 almost perfectly to our data. So if we could figure out that we have order 2, life would be great. Now here comes the tricky thing. Assume we have a very large polynomial degree. What happens here is so-called overfitting. So the polynomial tries to approximate all the data points as good as possible. So therefore it tries to match them all as good as possible. But if you now get new data points to your system, then they are not covered by the polynomial good anymore. So for example, assume another data point here, or for example here, then the polynomial cannot model it properly anymore. So this is something you probably heard about in machine learning. You have some training data and some test data. And if you fit the polynomial to the training data, then you add some test data, and the test data might be just the green dots I've printed down here. Then your polynomial fails. This behavior here is called overfitting, because it just fits actually the given data points too well. And we need to address this problem of overfitting how. And the answer to this is regularization. So we use it when selecting the polynomial degree manually does not work. And therefore what we're going to do is we choose a large order of the polynomial, but we'll reduce the magnitude of the parameters we do not need. So we can just assume in the case of the example before, let's say polynomial order 10, but then we try to keep the features of 3 to 10 down so that they do not have any negative influence to our data. This thing here works, or regularization in general, works very well if you have a lot of features. The cost functional, of course, changes when we add regularization. Compared to before, on the left-hand side, we still have our least square fit, but on the right-hand side, we now add a regularization. So the left thing is called data fidelity term, and the right is regularization term, and lambda here is regularization parameter. Obviously, if you set lambda to 0, then you end up in the previous problems. So therefore, only lambda greater than 0 makes sense. Otherwise, adding regularization doesn't really make sense. Also, adding a negative lambda doesn't make sense because it would do the opposite thing. It would just increase the magnitude of the parameters here. So I've written down here one example of regularization, adding just the features squared. And what we do now, this lecture here and next lecture, we discuss a couple of different regularization methods. But we will start with the most easiest one and the most intuitive one. And the most intuitive one is called the Tikhonov regularization. So it's named by a famous Russian mathematician who lived in the 20th century. And what we do is we assume on the one hand a model problem, for example, not the least squares because adding regularization here doesn't make sense, but polynomial order 3, 4, 5, or whatever. And now we just not only solve the least squares problem, but as I said, regularization. And here we actually add the 2 norm of the parameters. And if you remember, we said for a vector m, if we have m given as an m-dimensional vector, then the 2 norm squared can be written either as the scalar product of m in itself or as the sum from 1 to n of all the mi squared. So once again, this lambda greater than 0 is called regularization parameter. And now the obvious question is, what are we going to do with this problem here? And what I'd like to do with you the next couple of minutes, I'd like to derive a solution if we assume the least square fit of a straight line. Of course, as I said, a least square of a straight line plus regularization doesn't make sense at the first glance because you cannot really get rid of features here anymore. But still, we tried for you so that you can see what's going on here. And I'm very excited actually about the next couple of minutes because I'm pretty sure in the end you will notice something we talked about already. So we come back to our famous model. We say di predicted should be some m1 plus some m2 set I. So the m1 and m2 are the unknowns, as always. And as always, set I is the value along the x-axis. We assume once again n points. And we know already that this leaves us with n equations. And like always, we build the total misfit. So first we have the things you know already. So we have the dia observed. We subtract the model and we take the square. But now we add the regularization to it. So what we do, like we always have done, we drop the observed in the notation and we start calculating. And we're gonna have some fun here. So we would like to minimize E, as always. And the difference we're gonna see will be in the last two terms here. So first, nothing really changed compared to the things we did before. So we can get rid of all the 2's in there. And we turn to some matrix notation. So for the first part, in the original version, we just had n, so the number of input points. Here we have n plus lambda. Same thing on the second diagonal here. We have zi squared with sum, like before, but we add lambda. So the off diagonal remains unchanged. As well as everything else. Yeah, let's copy this thing to the next page. So once again, like before, we have reduced this large problem consisting of n equations to a problem with 2 equations. And again, we do some rewriting. So we look at the matrix A once again. We can split it into 2 pieces actually. So we can get rid of the lambda. And the first part here in the sum is like with the original least squares, T transpose times G, but now we have plus lambda times the identity. Nothing changes for the right-hand side. So we get to the famous normal equations already. And with that, we get to the solution. And that's it. Now we need to discuss what this means. I mean, we started this topic of regularization because we said that if we cannot decide on the polynomial order or in general the order or the behavior of the function we're gonna fit, then we add regularization so that we can keep the features down. Then we performed a least square fit of a straight line with regularization, where we said actually it doesn't really make sense. When we fit a straight line to some data, I mean, what do we gonna get rid of? The best case we can get is that the data is just on a constant line, and we do not need the linear term at all. But then fitting to it would just eliminate the linear term anyways. So why did we do that? And if you look closely here, I said plenty of times during the lecture, we can do the stuff here only if the inverse of G transpose times G exists. So we said if it does not exist, we cannot do the thing here. But now there turns up this arbitrary value lambda. And please remember once again, we said lambda greater than 0 here. So what we can do is we can shift the eigenvalues of this 2 by 2 matrix away from 0. So assume one of the eigenvalues of T transpose times G would be 0, but then you add some lambda, you're away from 0, and you know already if the eigenvalues are not 0, you can invert and everything is fine. From a strict mathematical point of view, you can show that ill-posed inverse problems get at least solvable when you add proper Tikhonov regularization with a regularization parameter sufficiently large. And this is the same we have written down here. We said when we add regularization, we choose the parameter large enough, then we get away from the 0 eigenvalues and life is good. So this is probably a lot to process. I do not need you to understand the depths of the thing I just said. But it should give you just another perspective to why we are doing regularization. And it's not just overfitting, but it's also getting problems. I would say getting problems well posed. So last two things we need to discuss today. We can also choose a more general Tikhonov regularization. And you notice that the change here is the parameter or operator lambda here with an arbitrary operator. So of course, for the identity matrix, then it would be the Tikhonov regularization we just introduced. And as I said, please remember that when you use the identity matrix, so thing which I did, then you shift the singular values away of the matrix. Good. This was it for today.